Well, good morning. So we're going to start right now with the binomial expansion, which we are hopefully familiar with at this time from other classes, going all the way back actually to remedial algebra. And it's the concept if I say I have a plus b, I have a plus b to the second. Actually, let's start with a plus b to the 0th, actually, and then a plus b to the first, and a plus b to the second, and a plus b to the third, and let's say a plus b to the fourth. Let's go this far. Well, that would be 1, that would be a plus b, that'd be a squared plus 2ab plus b squared, a cubed plus 3a squared b plus 3ab squared plus b cubed, a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth, and so on and so on and so on. Now, hopefully we have some awareness of how to expand a binomial raised to successive integer powers. I don't need you to memorize results, but we have to know where the numbers come from. So if I say, let's just consider the coefficients, ignore the a and the b for a moment, and let's just think about the coefficients. Then if I write all the coefficients down, I would see the following pattern. Now this pattern goes forever, obviously, because the next would be a plus b to the 5th. In fact, just for fun, can anybody tell me, right, 1, 4, 6, 4, 1, those are my coefficients. Can anybody tell me what the next set of coefficients would be? Anybody want to try that? Okay, I'll do my part. 1, 1. Okay, that's, in fact, how about if I do this part too? 5, 5. See kind of a pattern here. Anybody want to try the middle ones?
10, 10.
10 and 10. Now, how did you get that? What's the easiest?
Because you told me this in another class 2 days ago.
You just add those two together, right? You notice that? Okay. Now, this goes forever and ever and ever and ever. We know that. And somebody other than Tom, because Tom's heard this recently, what do we call this expansion that goes on forever and ever and ever? Anybody, most of you have heard this. What's this called, this set of numbers? No one?
Pascal's triangle.
Pascal's triangle, which is awesome because I can actually tell you the coefficients of every single conceivable binomial expansion of integers. The problem is if I want a plus b to the 99th power, then I need to know the row for 98 first. So in other words, this is a recursive definition. We were only able to do this because we had the numbers in the preceding row. But what if I wanted these numbers in general? Well, then there's something I absolutely need to recognize. Let me take this row right here. Okay. What do I know about the 1 and all that, all the numbers involved? Well, we got the 1, the 4, the 6, the 4, the 1. But if I do a quick check on my calculator, this is simply 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. The coefficients of the binomial expansion are combinations, not because I said so, but that's what we see evidence of. When you actually multiply this out the long way and then gather terms, this is what you're always going to see. And this is something I would hope that you'd seen in a lower level class. So this is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. Notice that 5 choose 0 and 5 choose 5 are the same thing. 5 choose 1 and 5 choose 4 are the same. And we know that because we know that n choose r is the same as n choose n minus r. Okay, so if I have n distinct objects, r being less than or equal to n, and I choose r of them, that's equivalent to choosing the n minus r that I don't want. In other words, I'm going to pick 5 people to take to lunch today from the group. Let's say we have 40 people in the class. Well, isn't that the equivalent of me picking which 35 people I don't want to take to lunch? I mean, numerically, that should be the same answer. And it is, because the denominator of both of these is r factorial and minus r factorial. So we know that this pattern, right, it goes in both directions. We see the same numbers up and then back down again. So what that gives us is a very, very simple formula for the binomial expansion. So the formula is actually, again, this is for positive integer n. If I was raising this to the 0, it's just 1, so that's not really very interesting. And so we would end at n. So I'll use a k in this case. You can use anything. Okay. Well, I know that I'm going to start with the highest exponent. So I'm going to start with the n. So it's going to be a to the n. Well, not exactly a to the n minus k, b to the k. Oh, okay. So when k is 0, I have this one and b to the 0, because then at the other end, when k is n, I'd have b to the k and then, or excuse me, b to the n and then n to the 0. So this is the pattern of exponents, but the pattern of coefficients would therefore be n choose k. Okay, that's the binomial expansion. This formula has been around for a very, very long time, and we use it in many different ways. So if we wanted to expand something, it actually makes it fairly simple. So let's just say we want to do just the first few terms, let's say. So I've got something of the form, how about, let's say, a plus b to the 12th power. And I just want to write the first few terms. I don't want to write the whole thing, and that's too long. So what would the first term be? Well, I think the first term would be a to the 12th. I think we agree. I think the second term is going to be an a to the 11th b. Let's do one more. And I think the next term is going to be a to the 10b squared. We all agree with that. So what are the coefficients then? Well, this was 12 choose 0 or 1. This should be 12 choose 1 or simply 12. This should be 12 choose 2 or simply 66. I'll put ... and it'll end with, of course, b to the 12. I know that. So this would be a to the 12th plus 12 a to the 11th b. Excuse me, 66 a to the 10b squared, all the way down to b to the 12th. This is what the binomial expansion would look like. But calculating the coefficients should be utterly trivial. That's something that should be really, really simple for us. Okay, so that's kind of a nice one. So let me make it a little bit harder. What if I'll use something different? How about if I have 2x minus 3y? And I want to raise that to the, I don't know, let's say the 6th power. What does this look like? Well, in this case, think of replacing a with 2x and think of replacing b with negative 3y. So that would be the first term then raised to the 6th power. Plus 6 choose 1, this term raised to the 5th power, and then negative 3y raised to the 1st power. There's my a plus b to the 6th, a to the 6th, 6 choose 1, a to the 5th, b, plus 6 choose 2, a to the 4th, b to the 2nd. And you can see we can keep doing this. Plus 6 choose 3 times 2x to the 3rd, negative 3y to the 3rd, all the way down to finally negative 3y to the 6th power. So the fact that I had coefficients, the fact that I had a negative, that doesn't trouble us at all. So I think of this as a plus b, where my a is 2x and my b is negative 3y. And then clearly this will alternate as a result. So this is actually fairly simple.
Brown, I think on the second line, the first term minus 3y will be, sorry, 2x will be in 5th. Oh, it's because I think you wrote 3.
Yeah, 6, 5, 4, 3. It's supposed to be a 3.
Oh, I see. Okay, sorry.
Yeah. Yes, I'm. This is my a, if you will. A to the 6th, a to the 5th.
No, you're right. My mistake.
You're thinking way too far ahead, probably. Okay, now here's a different way of looking at this, or the type of question I might run into, because this is something that will show up in many situations. particularly this shows up in statistics a lot. All right, I've got something of the form, let's say 4x minus 6y to the 10th power, and I want to find the coefficient of x to the 7th, y to the 3rd. I want to find the coefficient of that. Now, first of all, is there a coefficient of x to the 7th, y to the 3rd? Is that actually going to be a term in this expansion? Well, let's see. If this is 10th power, we do notice one thing. And from the binomial expansion that we did earlier, every single term was of the same degree. Okay, in this case, 12th degree, 12th degree, 12th degree, 12th degree. So if I have an x and a y and the whole thing's raised to the 10th, then I actually should start with an x to the 10th. I should end with a y to the 10th, and every term should be 10th degree. So first thing is we do recognize, yes, there is going to be an x to the 7th, y to the 3rd term. Now, what will the coefficient of that be? Well, like the previous example, if I first just thought of it as a plus b to the 10th, then wouldn't the answer be simply what? Wouldn't the answer
Each
just be
10 choose 3?
10 choose 3? By the way, could you also say 10 choose 7? Would that also work?
Yep.
Yeah. Do you all agree that, oh, that's the answer? That would be a piece of cake. Problem is, that's only when the coefficients are ones. Oh, so I've got more at stake here than that. So looking at the previous example, my answer is going to be a little bit more. That would be the answer if the coefficients were 1, but the coefficients aren't 1. So the x to the 7th term will really involve 4x to the 7th, won't it? And the y to the 3rd term will really involve negative 6y to the 3rd. That's where the x to the 7th and the y to the 3rd will come in. And now I can throw in the 10 choose 3. So this is the actual term. So let's calculate this. 6 cubed, raised to the 7th, 10 choose 3. And this is kind of big, right? My answer is 424,673,280 x to the 7th, y to the 3rd. So my coefficient, wow, I'm sure glad I didn't actually have to multiply this out in order to get that answer. Never multiply it out to get the answer. That would take so long. You actually have a formula to go directly to that term. Now, if I really wanted to expand this, I could, but I would still use the binomial formula. So there is a term with an x to the 7th and a y to the 3rd, but those coefficients have to go along with it. Okay, everybody cool with that?
Professor, it'd be
Wouldn't it be
negative, right?
negative?
Whoa,
Yeah, that's what I thought.
oh, thank you. Yes, thank you. There should be a negative there. I left myself just enough space there. There, see, there's the negative. All right. Yeah, good catch. Good catch. So this process should not really be that taxing. So we want to be able to do this. Now, there's a really, really powerful and important result. So when we go back and I look at Pascal's triangle again, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Let's just go this far. I would like to add the numbers in the row. So obviously the first row would just be 1. I'll put it right here. The second row would be 2. The third row would be 4. This row would be an 8. This row would be a 16. Wait, what was the next row again? I think it was 1, 5, 10, 10, 5, 1. And that row clearly adds up to 32. I'm not a rocket scientist, but I play one on TV. I didn't know any better. I think I see a pattern here. Wasn't this the a plus b to the 0 row, a plus b to the first, a plus b to the second, a plus b to the third, a plus b to the fourth, a plus b to the fifth? Oh my gosh. Do you notice how the numbers add up to 2 to a power? Now that's just crazy, because didn't these numbers come from combinations? In other words, this row right here, let's just take that fifth row. Didn't that fifth row, didn't this come from 5, choose 0, plus 5, choose 1, plus 5, choose 2, plus 5, choose 3, plus 5, choose 4, plus 5, choose 5, and we're saying that equals 2 to the 5th power? That seems a little bit crazy, but that's true. So here's really the question I have in general. I mean, clearly I see a pattern, but that's not a proof. Will the row always add up to exactly 2 to the power? So let's just say sort of in general. When I have the row that looks like this, okay, n choose 0 plus n choose 1 plus n choose 2 plus all the way up to n choose n. I'm going to do that row. What are we claiming that's going to equal, by the way? What are we claiming if we actually see a formula here? What should
2 to the power of n.
2 to the power of n. I would like to prove this. Whoa. I'd like to prove this? Well, we can't prove it by example. And I'm not going to be able to do this one using any form of induction, but we can actually use what we already know. We know the following. We know that a plus b to the nth power is the sum from n equal, whoops, sorry. I used k before, sorry. K equals 0 to n, and choose k, a to the n minus k, b to the k. Okay, great. What if I did this? 1 choose 1 to the nth power. What if I did that? Well, I already know what this expansion looks like. We already did this. This is a to the n plus n, a to the n minus 1b, right? This goes on and on and on, all the way till we get to b to the nth. I mean, we know that. That's not really the question. What if I replace a and b with 1? I mean, if this is always true, does it matter what values I put in for a and b is my question. Can I put any numbers in there? What do you think?
Yes.
Yeah. Well, if I replace a and b with 1, then what am I going to get? Oops, sorry. 0 to n of n choose k, 1 to the n minus k, 1 to the k. But wait a minute, what's this? Wouldn't that just be 1?
Yep.
So that would mean it's just this. And well, what is this? That would be n choose 0 plus n choose 1 plus, oh my gosh, folks, there it is. Because what's 1 plus 1 to the n? Isn't that 2 to the n? We just did it. We proved it. Because 2 to the n is simply 1 plus 1 to the n, and 1 plus 1 to the n would be the binomial with 1s in there. That's the proof that every row of Pascal's triangle will add up to 2 raised to the exact same exponent that your expansion produced. That's a cool thing. This is actually used heavily in statistics. In probability situations, if you've had statistics, you understand the concept. Binomial experiment, and we're actually going to look at this next day. A binomial experiment is an experiment not where you're using binomial expansions. No, binomial experiment is an experiment that has actually 2 outcomes. And does anybody remember what we call the outcomes in statistics if you've had it? Doesn't matter what the experiment is, there's always 2 outcomes. I could be flipping a coin and counting the number of tails. I could be rolling the dice and counting the totals that are 7. I could be standing at a street light and counting the number of cars who run the light. Whatever it is I'm counting, there's 2 outcomes.
Is it a binomial experiment?
That's what I just said.
Oh, sorry, I thought you were asking.
No, so a binomial experiment, absolutely all binomial experiments, all infinitely many that exist, have the exact same 2 outcomes. What are they? I'm counting things. So every outcome is a success. If you've had statistics, you could not have possibly passed the class because of all the things you learn in stats. This is the only thing that you have to know from probability. A success or a
Failure.
failure. That's it. If the thing happened, it's a success. If it didn't, it's a failure. That's it. That's why it's called a binomial, because there's only 2 outcomes. Now, the probability of a success versus the probability of a failure may change. If I'm flipping a coin and I'm counting tails, then tails are a success and heads are a failure. What? Fail? I failed by rolling a heads? No, I'm counting tails. So anything that's not the thing I'm counting is not a success. So they call it success and failure. So if everything is a success or a failure, then everything is based on the probability of success. So if the probability of a success is one value, then what is automatically the probability of failure? Anybody want to try that one? Whatever the probability of success is, what must the probability of failure be?
1 minus that.
1 minus that, because those things have to add up to 1. Oh, okay. So, and the reason I'm mentioning statistics is this is where most people will be exposed to this really for the first time. But statistics, let's not forget, statistics is lower than remedial algebra in terms of the mathematical significance. So what we usually do is we call P the probability of success, small p, and then we usually call Q the probability of failure. And the only thing that matters is that P plus Q is 1. Okay, so that means if I do the same experiment n times, right? I'm going to flip a coin n times. I'm going to roll the dice n times. Whatever you're doing, you're going to do n times. Then what I'm always dealing with is P plus Q to the nth power. But since P and Q add up to 1, when I'm all done, everything must add up to 1. But I have it in terms of P's and Q's and the combinations. Okay, so then if I said, okay, I'm going to flip a coin 10 times, what's the probability of each individual outcome? We're going to be able to calculate that next day using nothing more than the binomial expansion, because the binomial expansion is actually pretty simple. There's nothing really complicated about it. So let's have fun. Let's do a kind of a simplification thing. I'm going to give you start with an easy one because I've asked some questions of this nature. Excuse me. This one here. I would like to, let me take an easy one here. I've got the sum from k equal 1 to n. Let me make sure I'm writing this down correctly. I'm sorry, from k equals 0, not k equal 1, sorry. K equals 0 to n of, let's say, 3 to the k power times n choose k. Okay. Yeah, that's what I want. 3 to the k power times n choose k. I can't read my own writing there. So if I were to expand this, what would it look like? What would this look like? Well, if k is 0, I have 3 to the 0. Let's just write it out. And then I'd have n choose 0 plus 3 to the first times n choose 1 plus 3 to the second n choose 2. Eventually, I'm going to have 3 to the n choose n. Okay. Wow, that doesn't really look very helpful. Yeah, I can calculate that. That's easy, I guess. That's 1. That's 1. So that's 1. And then this would be 3n. Okay, and this would be 9, whatever n choose 2 is. And then down the road, I'm eventually going to get 3 to the n, and that's times 1. I'm looking at that going, I just don't see that being particularly useful. What I'd like to do is write this as one single term, not as a sum of terms, one single term using the binomial expansion. Now there's a simple trick to this. Remember, what's the form of the binomial expansion? If I do this, then I know that I've got, I'll put that in front. I know I've got something that looks like this, a to the n minus k, b to the k. Okay, I know that's correct. That's not a question. Does this look like this right now?
No. Oh, well, yes.
almost does.
Yeah, I thought you were just going to change it up a little bit. And you just said
But does everyone agree that this looks at least
yes.
a little bit like this? What am I missing though? I'm
The
missing
B.
this. Can I create that out of nothing?
You just put a 1 there.
What if I use a 1? exactly. What if I did this? I'm gonna put this in front now. Okay. And I'm gonna put this here. What can I put in front? 1 to the n minus k. Now, are these equal? Stare at that for a minute and convince yourself. Are these quantities equal? All I did was insert 1 to a power. Okay, and that's a finite power. This isn't something from calculus where we have indeterminate forms and 1 to these infinities. And no, this is just 1 to an integer power. Did I change the value by inserting 1 to a power?
No.
Pretty sure that's cool. Now, isn't this exactly the form? In fact, this is exactly the form of what?
1 plus 3.
Oh my gosh. That means that this quantity right here is equal to what? 4 to the nth power. So remember how I expanded it a moment ago and it got big and long and ugly and I had 3's to powers all over the place? That was correct, but not entirely useful. Especially what if n were really large? Oh my goodness. Let's just do this. Let's pick a value of n. Let's pick something small. How about let's pick n equal, I don't know, 4. Let's say we used n equal 4. So, because I want to compare this to something. So if I went up to 4 of 3 to the k and choose k, all right? So that would be 3 to the 0. And I'm going to write the whole thing out. N choose 0 plus 3 to the first, and sorry, not n. Sorry. If I put I'm putting a value here. So n, I'm already saying is what? Sorry about that. Yeah, I'm already saying n is 4. There's no more n. Those are just the same finite value. K is the thing that's changing. So this would be 4 choose 0, then 4 choose 1, and then 3 squared times 4 choose 2, 3 cubed times 4 choose 3, 3 to the 4th times 4 choose 4. I'm only going that far. I don't want this to be long. Now, that doesn't look so scary because I now have a value here. That's my n. My n was 4. So if I calculate, this is 1. This would be 3 times 4. This would be 9 times 6. This would be 27 times 4. This would be 81 times 1. Okay, so now if I add these numbers together, 67, 175, that'd be 256. Oh, which by the way is 4 to the 4th power. Kind of cool. Now, I really don't want to do this ever again because what if n was large? But I'm just demonstrating how cool that is that we got the same result. So this is a very simple example of how you can use the binomial formula to take certain shortcuts. Like I said, in statistics, we use that fact all the time that 1 plus 1 to a power is simply 2 to a power, and that's what the rows have to add up to. So if I use any other numbers, it will also work. So kind of a cool thing. Now we're going to switch gears a little bit, and I'm going to derive what's considered a very important identity. I don't want to say formula. It's more of an identity. It's something that can be used as a substitution in certain cases. It's something called the inclusion exclusion principle. Okay. Now, I want you to think about this logically for a moment. This is not really complicated. All right. So I've got 40 people in the class, and I want to form a committee. Okay. And let's say the committee I want to form has 5 people. If I just said, how many ways can I form a 5-person committee? Okay. To form a 5-person committee, from the 40 students in the class. All right. So anybody want to tell me what's the answer to that? How many ways can I form a 5-person committee from the 40 people in the class?
4 to choose 5.
Before you choose 5, yeah, that's not really complicated. And let's see, what does that come out to be? 40 choose 5. Whoops, 40 choose 5. Fat fingers here. That's a lot. 658,808. Now, Tom's thinking about this problem here. And Tom's thinking, I don't really care about anybody else in the class. I want to know, am I on the committee or not? I mean, let's face it. This is one of the funny questions I get asked a lot of times after an exam. I'll have students say, oh, how did the class do? And I always laugh. I said, you could care less how the class did. You want to know how you did. Nobody ever starts by saying, how did the class do? Like, no, how did you do? Then you want to know how the class did because you'd like to know, did you do better or worse? So Tom's thinking about this. Okay, this 5-person committee, it comes with perks. I think you probably get a free car out of it, and an office and all this. So Tom wants to, am I on the committee? So now here's the question. Let's figure out this problem from a different point of view. Is it clear to say that on this choice, this is how many committees I could possibly form? Tom is either on it or he's not. I think that's a safe answer. So if I want to say how many committees is Tom on, how many committees is Tom on? Well, that would mean Tom's already on the committee and I have to pick the other 4 people. Does that make sense? So how many committees is Tom on? Well, that would mean Tom's on the committee and there's 4 other people. So of this 658,000, exactly how many of them are Tom on? Anybody want to guess? Because it's Tom matched with 4 other people.
Be 39 choose 4.
Okay, that's exactly how many committees Tom is on. Now, exactly how many committees is Tom not on?
Well, the big number less this one.
Of the 6,
Be 1 minus.
5, don't think formulas. Of the 40 choose 5, of 658,000 result, Tom is on this many of those committees. How many is he not on?
658,008.
No. In combinations, how many is Tom? If this is how many Tom's on, exactly how many is Tom not on? That means Tom is set off to the side. He's not on the committee. We're not picking him.
So it's 40 choose 0, maybe something like that.
It would be the 40 choose 5 minus 39 choose 4.
No. You can't say that as a single combination. I want one combination that says exactly how many committees is Tom not on. That means you took Tom and you say, Tom, we're going to put you
5
on.
choose 39.
Other way around.
39 choose 5. Yeah.
39 choose 5. Yeah.
Okay.
In other words, I said, sorry, Tom, you're going to go sit over there. We're not picking you today, right? You're not going to get picked for kickball today. So of the 39 remaining people, I'm going to form my committee of 5 from the 39 people that do not include Tom. Does that make sense now? These are all the committees that Tom is not on. These are all the committees that Tom is on because I picked Tom and I have to pick the other 4 people. And this sum I'm claiming is the same as this. So let's add them up first. So 39 choose 4. That's 82,251. 39 choose 5 is 1,757. And when I add those up, they will indeed add up to that number exactly. So this is why it's called the inclusion exclusion principle. If I want to know, I have n objects, I want to choose r of them, then every single element is either in the choice or it's not in the choice. Okay, so does that make sense? First of all, every single thing either got chosen or it didn't. It's that simple. So if it's in the choice, that means I have to choose the rest of the things. If it's not in the choice, then I choose everything excluding it. So this presents a formula.
Could you explain one more time the second term, 39 choose 5, please?
Yeah, this.
Like how do we, why is it 39 choose 5?
Sorry, let me rewrite it. Hold on a second. 39 choose 5. I
No, I mean, why do we take 39 and why do we take 5?
Well, if Tom is not on the committee, I still don't have a committee yet. I still have to pick 5 people, but I have to pick it from all of the people that are left when I exclude Tom. So this is all the cases I included Tom in the committee. So if Tom is on the committee, I don't pick 5 more people. I pick 4 more people because there's only 5 people on the committee.
Yeah.
This is the inclusion. Now I'm saying, no, Tom's not going to be on the committee. We're kicking him out of the room. There's still 39 people left, and I still have to pick my 5 people. So this is the inclusion. This is the exclusion. Does that make little sense?
A little.
So the formula is simply this. Now, is there a restriction here? Well, of course, because remember, R cannot exceed N. So certainly, so in this case here, we're saying, no, R has got to be, R isn't going to be 0. That wouldn't make any sense. So R is between 1 and -1. That's I have a restriction there because you cannot have a negative number. I cannot have a negative number in here. So R could be as small as 1. That's kind of boring though. But the inclusion exclusion principle, which I just explained, gives us this formula. And this formula is actually called Pascal's formula, which is probably the most vague, ambiguous name ever, because we have a Pascal's triangle, we have all sorts of formulas. So to simply say Pascal's formula, people can say, I'm doing a lot of formulas and Pascal is involved in a lot of things. This one is generally called Pascal's formula. Again, it's a demonstration of the inclusion exclusion principle. I have R objects. R is at least 1. I have at least one thing. If R was 0, none of this would make any sense. And I'm saying, okay, of my N, I'm going to pick R things. Great. So pick any one item among the N. This is all of the ways that item is included. This is all of the ways that item is excluded. And again, if the item is already included, then I need to pick one less than R from the one less than N that remain. If the item is excluded, then I still have to pick all R of them, but from the N-1 that remain. Okay, now I've given you an argument as to why that's equal. I did an example with a calculation, where Tom was my person that I was using. That doesn't prove the formula though. So let's actually prove this formula. So how do I prove it? I prove it using factorials. So I'm going to start with this side and see if I can conclude this side. And this is just a really good exercise in manipulation. So what is this side going to be? That's going to be N-1 factorial over if you have to
N-1 minus.
If you have to do that off to the side, do that. Then what's that? That's N-1 minus R plus 1. That's just N minus R, isn't it? Now, if all else fails, remember N minus R plus R minus 1 has to add up to N-1. That's how I know I did it right. And then the second one is plus N-1 factorial R factorial. And what goes in front of that?
N-1 minus R factorial.
Yeah, I'm gonna write it as N minus R minus 1. It's the same thing, but a little easier to interpret probably. Now, a common error that I see people doing, this is in every class that you ever do a proof. I have people, they'll write, I want to prove this. So the first thing they'll write is this equals this, and then it equals this. And then at the end, they'll got N choose R equals N choose R. If I'm trying to prove something is true and my first statement is to write down my conclusion, then there's actually nothing to write. And I don't say that jokingly. I'm done with my proof if I'm assuming the conclusion before I start my proof, which is why you never write the conclusion as your first step of the proof. It doesn't make any sense whatsoever. I want to prove to you that 2 plus 5 equals -4. So I'm going to start my proof by saying 2 plus 5 equals -4, and I'm going to go from here. I'm done because I already wrote my conclusion. Of course, that's incorrect. But if I write my conclusion first, there isn't any manipulation that can be done because you wrote something in an equation form. This is not an equation. This is an algebraic expression. It's a thing. I'm not starting by saying my thing already equals something else. I'm starting with this and nothing else. Now I'm simplifying this by writing it equal to this. Now I'm going to simplify this. Now I need a common denominator here. I don't have a common denominator. What's bigger, n minus r or n minus r minus 1? What's bigger?
N minus r.
N minus r. So my common denominator should involve the n minus r. What's bigger, the r minus 1 or the r?
R.
The r. So that
Would-
automatically is my common denominator. Oh, so how am I going to get there?
Would you multiply with the n minus r minus 1? Do
Let's start with this one.
just multiply by r?
Will that do it right there if I do that?
Yep.
And I'm going to write like this. So we know what that would give me then. R minus 1 factorial times r. That is r. Great. Over here, what do I need? This is 1 less than this. So if I multiply this n minus r over n minus r, then what is n minus r minus 1 factorial times n minus r? That would be n minus r factorial. That would be the equivalent of saying I have 9 factorial and I'm going to multiply it by 10. Doesn't that make it 10 factorial? Everybody cool with that?
Mhm.
That's what we're doing here. So if I multiply this by n minus r over n minus r, this is now n minus r factorial. Now my denominators are the same. So all I have to do now is consider the numerators. So this numerator is r times n minus 1 factorial. This numerator is n minus r times n minus 1 factorial. That looks so complicated. Should I distribute? No, I should factor. If I
Take
said
out-
I have something of the form ax plus bx, wouldn't that just be a plus b times x? What do you think? Is that true?
Yep.
So what do you mean? Well, look. I have thing times n minus 1 factorial plus other thing times n minus 1 factorial. So isn't that just the sum of my coefficients? Yeah. So this will be this plus this. I just added the coefficients. Oh, how convenient. I have n times n minus 1 factorial. What does that equal? Isn't that n factorial?
Yes.
And that, by the way, is the formula for n choose r. We have now proved it. We started with this. We concluded this. Could we have started with this and worked backwards? Could we have done that legally?
Yes.
Yes, but that would have meant you wrote this and then you would have had to know to do this. And then pull, you do see why that's way more complicated. We're trying to work the other way. The problem with starting with the more simplified term and working backwards means you have to introduce terms and then pull them apart and do all sorts of algebra. I don't think this is intuitively obvious that you would want to go this way and then do this. Yeah, I think that would be way too complicated. If I'm proving the formula is true, I just take one side, work it until I get the other side. Now, this is the formal mathematical proof of the inclusion exclusion property, but I like the verbal one because I love it if you can make that argument. So an item is either in or it's not. How many ways can it be in? How many ways could it not? And since those two things would be complementary, so I'm going to pick 5 people on committee. I think it's safe to say that Tom is either on the committee or Tom is not. That's it. That's black and white. I've made it binary. I've made it true, false, 1, 0, on, off. So how many ways could he be on? How many ways could be off? Now we could do that same thing with every single person, but that's not the point. We wanted to create 2 different situations that clearly add up to the whole, but for different formulas. Now, are there restrictions on this formula? Yeah, I said before, R has to be greater than or equal to 1 in this formula and less than or equal to n minus 1. Otherwise, I run the risk, if I don't put that restriction, of potentially having a negative number. You cannot have a negative number in a combination because you can't have a negative number in a factorial. Okay, I can have a 0 in the combination, right? Because I know that n choose 0 is just 1. That's okay. But I can't have n choose -1, right? There's no meaning for that one. So this is where we are. I think you're going to